Hi Calculus 1 students. This time we will tackle in the chain rule. It's an exercise, so you should try it out actually. I wrote example, but it's actually an exercise. And I'm going to be honest with you, it is algebraically difficult and tedious, but it's nothing you haven't seen before. Okay, so I'm giving you a function that, like, be prepared, its derivative is going to be a beast. And we want first to find all values of x for which the tangent line is horizontal. Then find all values of x for which f is not differentiable. And finally, well, number 3 is actually a bonus, okay? So I will tell you what. After number 2, if you want, you can actually close the video and forget about number 3. If you want, like number 3 is a bonus. So if you are interested to know like what is exactly happening at the values where f is not differentiable, then continue watching. The video will be long on purpose, but there will be like a point at which you can actually close the video if you want. Okay, so this is the function. Find all values of x for which the tangent line to f is horizontal. So we have seen now this a couple of times. So this happens when f of x is equal to 0. And remember, we will use a technique that's called simplify by factoring. Okay? And this technique pretty much tells you to factor the lowest exponent of each bracket, even if that exponent is negative. That's the one you want to factor. So factor out lowest exponent of each common factor. So here goes. The first step is to actually take the derivative of, and I told you that's going to be hard. Okay? So we're going to have to use, well, actually, we'll go step by step to begin with. So first off, we should write the function in a more suggestive way. Okay? So before taking the derivative, let's actually write e to the power of x squared over 2 plus x times 3x minus 1 to the power of 1/3. And using a rational exponent like this, using a rational exponent like this will actually help the differentiation. So let's go. So f prime of x. So I'm going to perform each derivative in, I will start it off in green, but we will use the outside-inside rule for the chain rule, right? So both of these derivatives will happen to use the chain rule. So you have a product, which means you do derivative of the first, but remember, this turns out to be a chain rule. So the inside-outside rule tells you that, the outside-inside rule, sorry about that, I messed up the order. So it's that you take the derivative of the outside. Now the derivative of e to the u is e to the u, right? So then you stick the inside in, and you multiply the result by the derivative of the inside, which is in this case, so 1/2 multiplied by 2x plus 1. Okay, so that's the derivative of the inside of e to the. Now this is multiplied by the second term, to which we don't take the derivative. We continue the product rule. We have e to the power of x squared over 2 plus x. And then we use the outside-inside rule for this part as well. So now the inside is 3x minus 1. So you're going to have here 1/3 bracket to the negative 2/3. The inside is 3x minus 1. And finally, you multiply this by the derivative of 3x minus 1, which is just 3. Okay. It filled the entire board. I'm actually happy I was able to write it in a single board. Okay. Now, one thing that you can see is, okay, well, we could do some kind of simple simplification like this 3 and this 3. That will help. 3, sorry about that. But at some point, you want to factor the lowest exponent of each common factor. So how do we achieve that? So here, note that the exponential itself is a common factor, right? So we're going to take it out. Okay, so we have, I'm going to write it here. So we're going to have e to the power of x squared over 2 plus x. Okay, so this is one of the common factors, by the way. Then another common factor turns out to be this. But it doesn't have the same exponent, so that's what I'm talking about. So what you want to do is to factor the lowest exponent of it, which is here, the negative 2 over 3. So that's going to become 3x minus 1 to the power of negative 2 over 3. After that, there's nothing else to factor. So now you're going to open the big brackets. And now what's going to happen is you have this, which turns out to be x plus 1. And now, okay, here be slightly careful. So what you have to do is to subtract the exponents. Now, just because of the structure of the derivative, you know that when you use the power rule, you decrease the exponent by 1. You know automatically that this will have exponent 1 higher than this. But keep your eye on the ball, right? Make sure of that. So you multiply this x plus 1, which comes from the red term over here, by 3x minus 1. And just to tease you, like to the power of 1. But eventually, we are dropping that 1, obviously. Now, what's nice is that here, nothing else remains. You just have plus 1. Okay. Now, at this point, I'm going to erase, I think, I'm going to erase even the example, right? I'm going to erase the instructions. So where is my eraser? It's right here. Perfect. Okay. So what you want to do is just expand and refactor. So we're continuing. Now I'm going to drop the color code over the common factors. We have e to the x squared over 2 plus x. One thing you can do is to actually bring this at the denominator, and this will become important for your interpretation. So make sure that you have positive exponents whenever you simplify your derivative. And then I will just put it as a square bracket just to show you that what we have is actually here. But what we do is we expand. So we have 3x squared. So we begin here with 3x squared. And now we have minus x plus 3x. So plus 2x. And now finally we have minus 1 plus 1. So we are left with this. We finally factor this, okay? So as you can see, we have a common factor of x. So final answer will be, let's put it as a big fraction. Okay, so the exponential multiplied with x, multiplied with 3x plus 2, and then all of this divided by 3x minus 1 to the power of 2 over 3. So this is the derivative. Now it's time to answer all of the 3 questions. So question number 1 is to find out where the derivative equals to 0. So we're solving, that's it, solve f prime of x equals to 0 for x. So in other words, we take this big thing and we set it equal to 0. And actually here, just to win a little bit of time, note that the denominator of a fraction can never make the fraction 0. So overall, you will always set up the numerator to be equal to 0. Now let's have a look at the solutions. Okay, so ask yourself if this factor could be 0. The answer is no. Okay, because it is an exponential. So e to the y is positive for every y. Okay, so this can't be 0. So this sub-equation has no solution. And actually, let's erase this. It might get in the way. Okay, but you have two solutions that are coming from here. So from this factor, as you can see, x could be 0. And finally, from this factor, you have that x could be equal to -2/3. So in other words, you've got your answer for number 1, x equals 0 and x equals to -2/3. For number 2, you want to figure out where the derivative does not exist. So find values of x for which f prime of x does not exist. So this is a formula for f prime of x, and it is valid for every value of x except one of them. And that's basically the value that we're looking for. Okay, so this happens when, for example, the denominator is equal to 0. So when denominator is equal to 0. So in this case, this happens when 3x minus 1 to the power of 2/3 is equal to 0. And solving that equation is quite easy. It will happen when x is equal to 1/3. And actually, I'm going to write it over there. Okay, at this point, if you want, you can close the video because I'm covering the bonus. So now, why is it possible? Like, what is happening at x equals 1/3 for the function to fail to be differentiable? So it being at the bottom gives us a very good hint. It gives us the hint that we probably have a vertical tangent line. So so what we're going to do is we're going to find the limit as x is approaching 1/3 of, remember, the absolute value of f prime of x. So in other words, it's the limit as x is approaching 1/3 of, so we have it over here. So that's going to be, okay, yes, let's actually put up everything in an absolute value. That I think is a great idea. So we'll have here this plus x. Okay, then we have like x, and then we have 3x plus 2. And all of that is divided by 3x minus 1 to the power of 2/3. All of this to say that what you're going to end up doing is, well, here you cannot exactly directly substitute because you're going to have a 0 at the bottom. Okay, so whenever you directly substitute, what you're going to find out is that you're going to have like non-zero over 0. And if I'm not mistaken, this is actually enough to show that you have a vertical tangent line because the function is continuous at 1/3. Okay, so this shows that f has a vertical tangent line at x equals 1/3. 1/3, not 1/2. Since f is continuous at x is equal to 1/3. And you can easily see this by the function itself. If you go back at the very beginning when I wrote down the function, you will notice that if you actually take the limit as x is approaching 1/3, which is easy, it's a direct substitution limit, you will see that this direct substitution is working, which means that the function is continuous. So, but you do need to ensure that the function is continuous in order to be able to say that a non-zero over 0 here turned out to be a vertical tangent line. All right, I hope this helped. See you in the next video or in class.